Alrighty. Well, as far as the relationships to momentum and energy in a relativistic regime, we have to be very careful, especially in the cases of photons. So let's dive into this question. The statement reads, in the past, most experiments in particle physics involved stationary targets. One particle, usually a proton or an electron, was accelerated to a high energy E and collided with a target particle at rest. Far higher relative energies are obtainable with the same accelerator if you accelerate both particles to energy E and fire them at one another. Classically, the energy E bar of one particle relative to the other is just 4E. Why? Not much of a gain, only by a factor of 4, but relativistically, the gain can be enormous. Assuming that the two particles have the same mass, m, show that E bar is equal to 2E squared over mc squared minus mc squared. Okay, so here, suppose that you use protons, which have a rest mass of mc squared equal 1 giga-electron-volts, with E equal 30 giga-electron-volts. What E bar do you get? What multiple of E does this amount to? Here, 1 GeV, or giga-electron-volt, is 10 to the 9 electron-volts. Okay? As always in physics, let's go ahead. Alright, so let's draw it out. What we see here is that in A, we have the classic experiment where we keep one target particle stationary, and E is the energy of the other particle that's going to smack into it. Versus B here, which is something that all the particle colliders use now, things like the Atlas experiment, things like the Fermi lab, or pretty much any other accelerator. We get much larger energies. Now let's see how. Both of them are traveling together and want to smack each other with E, but of course in a relativistic regime, this becomes way more than what we'd expect. So let's see how to deal with this. All right, so now that we are trying to solve for this, let's first understand that classically, for a moving particle, we had that E was equal to 1/2 mv squared. So in a colliding beam experiment, the relative velocity classically is twice the velocity of either one. So we just simply put V goes to 2V in the energy equation. So we see that E prime is equal to 1/2 m times 2V squared. So we have to square everything inside the parentheses. Hence, we end up with a 4V squared factor, and a factor of 4 comes outside from that, and that's how we end up with 4E. That's a pretty typical scaling law. However, now we have to incorporate the relativistic regimes for the energies and speeds that these particles travel at. So now, to solve the rest, we need to define the frames. Of course, with everything that we do in relativity, our frame definement is the most important. So let S bar be the system in which 1 is at rest and its speed V relative to S is the speed of 1 in S. The Lorentz transformation tells us that the P bar naught is equal to gamma P naught minus beta P1. Again, this is the Lorentz transformation for the momentum energy 4 vector. And that goes to E bar over C is equal to gamma times E over C minus beta P, where P is the momentum of 2 and S. Okay, so I said a lot of words. Let's go see what these look like. Here we have the frame that was originally the picture that we were looking at in part of the picture B frame that we were looking at, where both particle 1 and particle 2 were coming together head on, and that happened in inertial frame S. Now we're going to transform this framing to where S bar is moving at the V that E was going to have, that the particle 1 was going to have due to E. So we see that the frame itself is moving at velocity V, and 1 therefore looks stationary in this frame. And so all we have is an E bar here to calculate and show that the E bar is on 2. All right, so let's see how we can manipulate this now. All right, so in S bar, 1 is at rest, and thus E equal gamma mc squared, or the rested mass energy, where gamma therefore is equal to E over big MC squared. Similarly, P is equal to negative gamma mv. Okay, so if we plug in the v, or the big velocity, transform velocity, we see that that's equal to beta c. Therefore, if we want to find out what E bar is on particle 2, we have from 2 slides ago, E bar is equal to c gamma, the speed of light, E over c minus beta times negative gamma big M beta c. So we have a lot of c's, a lot of gammas. Let's go ahead and consolidate. So we distribute the c in, so E is standing by itself, and we have a c squared in the bracket term. The two negatives cancel, and we're left with a factor of gamma m beta squared c squared now. Pretty easy to deal with. But we note that beta being v over c is very quickly relatable to gamma via the Lorentz factor. So we just square both sides, and then we solve for what beta is in terms of gamma, or beta squared is in terms of gamma squared. So it makes our life easy. With this, we see that we know that E bar is equal to gamma E plus the gamma squared, since we're distributing in the gamma now of the earlier equation. And so now we can shove the beta squared term in, and we see that the gamma squareds cancel. That being said, we know that gamma squared from the relationship we solved up top is equal to something in terms of E. So we can plug in everything we need to in terms of E and get rid of gamma completely. So as you see here, we get a whole ton of substitutions via the gammas, and we need to be very careful how do we simplify this. Our first substitution leads to E squared over big MC squared over the rest mass. So we got our E squared there. And we see here that the rest mass terms cancel on this other term. So we're just left with a E squared over MC squared. Pretty cool there. And then minus a big MC squared. So in actuality, we have two terms of the E squared MC squared. And hence we see that E bar is equal to 2E squared over MC squared minus MC squared, which is exactly what we started with in the statement. So we were able to solidify this. That being said, we had to use the transformation rules of the 4-vector with the Lorentz transformation, and we also had to use some clever geometry. So just be careful when you're setting these up, because the substitutions kind of seem a bit messy and can definitely get out of hand pretty quickly. Fair warning. That being said, now that we've proven that this is the boxed relationship that we were trying to, let's go ahead and plug it in. So if we plug everything in that we need to, MC squared is equal to 1 GeV, so we'll just plug in 1 for that. So we get 2 times 30 squared over 1 minus 1 is equal to 1799 GeV. If we divide that by the GeV of 1 proton, we see that we get a factor of 60E, which is far greater than 4E in the classic realm, and thus we see that the relativistic regime gives us more insights and more ability to discover things that we didn't before. How fascinating.